Let's learn about numerical integration techniques. Okay, so basically we are looking at how to solve an integral of this type. Okay, so basically we are looking only at definite integrals and how to solve them numerically. Okay, we are going to learn how we can get a value for this integral without actually applying the integration techniques or integration formula, but by calculating some values. Okay, obviously as in other numerical techniques, the answer is not an exact answer, it's rather a approximate answer. Okay, so it's going to have some degree of error. Okay, let's just say that I have my function of x, which is this one, and I'm supposed to find out the integration fx from x is equal to a to x is equal to b. Okay, to arrive at a solution using a numerical technique, what I'm going to do is I'm going to divide this interval from a to b into n small intervals, each having a width of h. Okay, so I'm dividing the interval into sub intervals. Okay, so let's just say that my a is x0. Okay, then this guy would be x0 plus h, right? This guy would be x0 plus 2h and so on. Finally you are going to have your b as x0 plus nh. Okay, so my integration is now from x0 to x0 plus nh fx dx, right? So my integration a to b fx dx is now equal to this guy. Okay, now as we have seen in the interpolation techniques, my f of x can be written as f of x0 plus ph, right? So what I want to do is I want to make a substitution x is equal to x0 plus ph in this particular integral. Okay, when I do that, what I have is dx is equal to, this is a constant, so you're going to have h into dp. Okay, and when you have x equal to x0, your p is equal to 0, and when you have x equal to x0 plus nh, your p is equal to n. Okay, so you have this transformed into integral 0 to n f of x0 plus ph, and instead of dx you have h into dp. Since h is a constant, I'll just keep it outside and I have dp. Okay, now my Newton's forward integration formula tells me that this is going to be equal to integral h into 0 to n. You expand this using your Newton's forward integration formula, you have f of x0 plus p into delta f of x0 plus p into p minus 1 upon 2 factorial delta square f of x0 and so on. Okay, now you have this to be integrated with respect to dp. Okay, so you have your p's over here, you can integrate them term by term. Okay, so you have h into, integrate this guy with respect to p, this is a constant, so you're going to have f of x0 into p. Okay, plus integration of this guy is going to be p square upon 2 delta f of x0. Okay, plus you integrate this, this is your p square minus p. Okay, so it's gonna be p cube by 3 minus p square by 2 upon your 2 factorial, and then you have your delta square f of x0, okay, and you have your rest of the terms, delta cube terms, delta raised to power 4 terms, and so on. You are integrating between limits 0 to n, okay, so you now have to replace p with n. So what you finally have is, this is equal to n into h y0, f of x0 is y0, okay, y0 plus n by 2 delta y0 plus n into 2n minus 3 by 12 delta square y0 plus you are going to have a delta raised to power 3 term also, okay. So when you are going to integrate that particular term, you are going to get n into n minus 2 whole square upon 24 delta cube y0, and you are going to have more terms like this, okay. So essentially your integration fx x0 to x0 plus nh comes out to this, okay, and this particular formula is known as your Newton-Cotes integration formula, okay. So that's the Newton-Cotes integration formula. Now on the basis of this particular formula, we are going to derive few other formulas that help us to numerically integrate a given function, okay. I can simplify this formula if I can say that my fx basically approximates to a polynomial of degree 1, okay. If my fx approximates to a polynomial of degree 1, then I know that all the differences having degree 2 or more are all going to be 0, okay, or having order 2 or more are all going to be 0. So this is going to be 0, this is going to be 0, and all the next terms are going to be 0. So what I'm saying is, I just need 2 values to find out a polynomial of degree 1, okay. I need x0 and I need x0 plus h, okay. These are the 2 values. So essentially what I am saying is n is equal to 1, okay. So when n is equal to 1, I am approximating my function to a polynomial of degree 1, and what I get from that is integration x0 to x0 plus h. Since n is equal to 1 over here, you are going to have x0 plus h fx dx is equal to, n is equal to 1, so you have h y0 plus n by 2, which is 1 by 2 delta y0 plus all other terms are 0, because this is a polynomial of degree 1 and your forward differences or second, third, fourth and all higher forward differences are going to be 0, okay. So you have basically this, okay. Now you know what is delta y0, it is y1 minus y0. So you have h into y0 plus half y1 minus y0, okay. So over here you have a y0 present and over here you have a minus half y0. So this is equal to h by 2 y0 plus y1, okay. Now if you look at the original problem, it is something like this. You are supposed to find out integration from x0 to x0 plus nh. Okay, you've got integration from x0 to x0 plus h. Okay, over here you've got integration from x0 to x0 plus h as equal to this. Similarly, integration from x0 plus h to x0 plus 2h is going to be what? You can just assume that this is now your x0 and this is now your x0 plus h. Okay, so over here your integration x0 plus h to x0 plus 2h is going to be, you have fx dx is going to be h by 2 into y1 plus y2. Okay, when you are having x0 you have y0 plus y1. Okay, so when you are having x1, which is this guy, you are going to have y1 plus y2. Okay, similarly, what is your integration from x0 plus 2h to x0 plus 3h? It is going to be equal to h by 2 into y2 plus y3. Okay, so your integration from x0 to x0 plus nh is basically composed of integration from this to this plus this to this plus this to this and so on, right? What is the last subinterval? The last subinterval is this, which is x0 plus n minus 1 into h to x0 plus nh. Okay, so over here the corresponding y value is yn minus 1 and over here the corresponding y value is yn. Okay, so when you're going from x0 to x1, your integration is this, y0 plus y1. Okay, when you're going from x1 to x2, your integration is this. So when you're going from x0 plus n minus 1h to x0 plus nh, your integration is going to be equal to h by 2 into yn minus 1 plus yn. Okay, so what you have is your integration a to b fx dx, which is equal to integration x0 to x0 plus nh fx dx, which is equal to integration x0 to x0 plus h fx dx plus integration x0 plus h to x0 plus 2h fx dx and so on up until integration x0 plus n minus 1h to x0 plus nh fx dx is going to be equal to, this is h by 2 y0 plus y1. Okay, this is h by 2 y1 plus y2. Okay, similarly you are going to have, for this guy it's going to be h by 2 yn minus 1 plus yn. Okay, so what you're saying is you have your y value present over here, that is your y1 value present over here and over here also. You're going to have a y2 present over here and in the next term also. So this result comes out to be equal to h by 2 y0 plus yn, which is present only once, plus 2 into y1 is present twice, y2 is present twice, yn minus 1 is present twice, so you have plus 2 into y1 plus y2 plus y3, so on up until yn minus 1. Okay, So what are these y1, y2, y3? These are the values of f of x at x1, x2, x3 and so on, okay, which is at x0 plus h, x0 plus 2h, x0 plus 3h and so on. So what you have over here is known as the Trapezium rule, okay. This is your Trapezium rule. So what's happening over here, just understand, you have a function, okay, and you're supposed to find out the integration of this guy between a, which is this point, to b, okay. So what you do is you make n small intervals, okay, and now you have the formula which is this. What you're doing is you're approximating the function between one subinterval as a polynomial of degree 1, okay. What is a polynomial of degree 1? Y is equal to ax plus b is a polynomial of degree 1 which is a straight line, okay. So what you're doing is you are approximating this region as a straight line. Similarly, you're approximating this curve as a straight line. You're approximating this curve as a straight line, and the same is happening over here. So essentially what you're having is a trapezium, okay. This is a trapezium. You have two parallel sides present, okay. So everywhere you have a trapezium and you are assuming that your subinterval is essentially a trapezium and you're calculating the area of that trapezium, okay, and that's your trapezium rule. Obviously it's not going to give you exact answers, you have some error, okay. So that's the error. So this is the error. So you're not going to get a perfect answer, but you're going to have some degree of error because you're approximating this curve to be a straight line, okay. So that's your trapezium rule, which gives you integration fx dx from a to b as equal to this thing, okay, which is you calculate your y at x0 which is going to be y0, you calculate your y at x1 which is going to be y1, calculate your y at x2 which is going to be y2, do this up until yn and just apply this formula and you will get the value of integration from a to b, okay. Let's take an example. Now we want to find out the integration e raised to power x square dx from x is equal to 0 to x is equal to 2, okay. We are supposed to take 10 intervals to find out the value of this integration. So essentially it is given to us that n is equal to 2. So how you are going to proceed? It's very simple. Just create a table, okay. You have your x, you have your y which is your f of x which is your e raised to power x square, okay. So you have your y which is your e raised to power x square. It is given that we have to take n is equal to 10. So my h is going to be what? H is going to be 2 minus 0 upon 10, okay, which is 0.2, okay. So you are going to calculate your x and y values for x equal to 0, x equal to 0.2, 0.4, 0.6, 0.8, then you are going to have 1.0, 1.2, 1.4, 1.6, 1.8 and 2.0, okay. So you have 10 intervals, okay. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, okay. just calculate what is y at e raised to power 0, e raised to power 0.2 square, e raised to power 0.4 square, and so on, and you are going to have your y0, y1, y2, y3, and so on up until you are going to have your y10 over here. Okay, and once you have all the y values, you are just going to apply your trapezoidal rule, which is this. Okay, now instead of yn you have y10 because n is equal to 10. So your final formula is going to be y0 plus y10, y1 plus y2 plus y3, so on up until yn minus 1, which is y10 minus 1, which is y9. Okay, just putting the values of all the y's over here, you have your h as 0.2, and whatever is the final result is the value of this integral. Okay, the final result basically comes out to be 17.0621. Okay.